Supplementary material video for HAL3D. On this video, we show how our tool can be used to label parts of various shapes. For illustration, we will use this set of chairs from PartNet. Initially, the input shapes are decomposed into parts. Here we show the parts with different colors. The labeling proceeds hierarchically, following a tree structure that organizes the hierarchical part labels, from coarse labels, top, to fine-grained labels, bottom. The labeling process starts at the root node. Let's first watch how our method can be used to label shapes at this node. The active learning procedure will label all shapes in the input set iteratively. In this example, the input at the root node is a collection of chairs. On the first iteration, the label proposal module predicts labels for each shape, illustrated here by using unique colors for each label. These label proposals are ranked by their label probabilities. High confidence proposals, like the ones at the top, are passed to the verification step. Low confidence proposals go instead to the modification step. Remaining shapes are skipped in this iteration and are instead processed in the next one. Let's now watch how the verification process looks for the high confidence proposals. Here the user is tasked with checking if the labeling is correct or incorrect, indicated by the smile or frown icons. For our chair example, the root has 6 children, so there are just 6 part labels to verify. To make the task easier, each part label is assigned a distinct color, enabling the user to rapidly determine whether the label is accurate or not. Next, let's watch how the shape modification tool is used to fix the low confidence proposals. In this tool, the user edits one shape at a time, assigning the correct label to any incorrectly labeled parts. The user first selects the incorrectly labeled part, then selects the correct label from the dialog. Since the chair has only 6 labels at the root node, the network can attain greater accuracy in label prediction compared to non-hierarchical designs. After verification and shape modification, we gather the correctly labeled shapes and incorporate them into the training set to fine-tune the network. Once the network has been fine-tuned, the first iteration is completed and we proceed to the second iteration. On the second iteration, the only difference is the input is the set of unverified shapes. That is, the set of shapes we skipped on the previous iteration together with the set of shapes that failed verification. Following iterations work likewise, using as input the remaining unverified shapes. The process repeats until all shapes have been approved by human verification or modification. Here we have the final labeled shapes at the root node. The labeling procedure continues now on the subsets of each label. We will show this step using the chair base, shown in blue, as an example. Note that the chair base is a node of type OR. It indicates which type of base chair it is. This time, the input is the subset of shapes that were labeled as chair base. We use the pre-trained label proposal module to predict part labels for them. Since the chair base is a node of type OR, this time we use a classification network. The classification network will assign a single label to each chair base shape. Once we have predictions, the procedure is the same as before. We sort the proposals into high confidence, low confidence, and skipped shapes based on label probabilities. The verification step is the same as for the root node. However, since we are dealing with a node of type OR, all parts from a shape are assigned the same label. This makes it easier for users to identify which shapes are incorrectly labeled. The modification step is simpler too, as the user needs to choose a single label for the whole set. After the verification and modification steps, the procedure continues in the same way as it did for the root node. The verified and modified shapes are used to fine-tune the label proposal network, and the process repeats until all chair bases pass human verification or modification. Here are the labeled results at chair base node. Once we complete the active labeling process for the chair base node, We further split the shapes into several subsets and use them as input for the active labeling procedure at the children node. Take the regular leg base for example, which is the children node of chair base node. Once we complete the active labeling process for the chair base node, we obtain a subset of regular chair base shapes. We will use the same tool and iterative labeling process to assign children label to each regular leg base shape. Here are the part label verification process at regular leg base node. Here are the part label modification process at regular leg base node. The labeling task at each node requires assigning a relatively small number of labels, and the use of distinct part colors facilitates accurate labeling by users with high efficiency. Here are the final labeled results at regular leg base node. Note that the children labels at regular leg base node are leaf node labels. Once the leaf node label is assigned to a part in the tree, it will be output as the final result for that part and will not undergo further labeling. The hierarchical labeling process will continue until all parts have been assigned one of the leaf node labels. Here are the final labeled results after finishing labeling at all internal nodes. The duration of the fine-tuning process varies depending on the number of parts at each node, ranging from 20 minutes to 3 hours. However, users don't need to wait for the fine-tuning to complete as the active labeling can be performed in parallel at different nodes. If there is no parent-child dependency between nodes in the tree, the active labeling process can be parallelized across these nodes. This means that users can work on labeling different parts of the object simultaneously, which can speed up the overall labeling process. For example, while the label proposal module for the chair back node is being fine-tuned, users can simultaneously perform verification and modification at the regular base node. Thank you for watching.